Scientists have just confirmed something extraordinary. 3I/Atlas, an interstellar object the size of Manhattan, has accelerated through our solar system at 170,000 miles per hour without shedding any detectable mass. Its brilliant blue luminescence and non-gravitational trajectory violate every established principle about comets. If the predicted 5 billion-ton gas cloud fails to materialize, physics itself faces scrutiny, and the implications extend far beyond the field of astronomy. What force is propelling Atlas forward, and what information is being withheld from the public? Avi Loeb, a professor of astrophysics at Harvard University, has emerged as one of the most prominent voices in discussions like these, not because he claims to possess all the answers, but because he demands evidence before endorsing any theory. In the early days of the 3I/Atlas phenomenon, Loeb startled his colleagues by estimating the probability of a technological explanation at as high as 40%. That assessment came before the data deluge began. Now, after years of controversy surrounding his research on Oumuamua, Loeb advocates for a different kind of scientific rigor. He characterizes our encounter with 3I/Atlas as a blind date. You arrive with an open mind, you observe carefully, and you refuse to draw conclusions before gathering sufficient evidence. We are on a blind date with 3I/Atlas, he explains. Do not fall in love before you see the face. This philosophy isn't about suppressing curiosity. It's about preventing expectations from distorting observations. Loeb's public lectures and private communications reveal a delicate balance. He cautions against both sensationalizing the extraordinary and dismissing the unexplained prematurely. The principle is straightforward. Allow the object to reveal itself through data and ensure measurements precede media coverage. This methodology transcends academic prudence. It's a framework that influences how scientists, journalists, and the general public approach every new anomaly. For Loeb, the 3I/Atlas story represents a test of scientific process as much as physics itself. He champions transparency, open data access, and a willingness to revise beliefs as new facts emerge. Ultimately, what matters isn't how bizarre the object appears, but how robust the evidence becomes. With 3I/Atlas, the guideline is unambiguous. Observe first, conclude later. That's the only path to determining whether we're encountering a cosmic visitor or simply witnessing nature at its most inventive. At its foundation, 3I/Atlas is a Manhattan-scale object measuring approximately 1.8 kilometers across with an estimated mass of 33 billion tons. It entered our solar system along a hyperbolic trajectory, traveling at nearly 170,000 miles per hour. On October 29th, it swept past the sun at perihelion, triggering a worldwide campaign to capture every available measurement. What emerged has left researchers grappling with 9 distinct anomalies, each supported by concrete data. First, the trajectory. 3I/Atlas exhibits non-gravitational acceleration at levels far exceeding what solar radiation pressure can account for. NASA's Jet Propulsion Laboratory database records this acceleration at more than 5 standard deviations above expected values. Standard comet models will require the object to expel nearly 1/5 of its total mass in gas and dust to produce this effect. Yet there's no evidence of a 5 billion-ton cloud trailing in its wake. Second, its coloration. Most comets trend toward red hues, dominated by dust and carbon-rich compounds. Atlas, conversely, shifted toward blue as it approached the sun, a rare spectral signature confirmed by ground-based and space-based spectrophotometry. The blue peak coincided precisely with perihelion, the exact moment when a craft might execute a high-speed gravitational slingshot maneuver. Third, rapid brightening. The object's light curve spiked faster and more intensely than model predicted, dramatically outpacing standard outgassing projections. Photometric observation campaigns tracked the surge but detected no corresponding increase in gas emission lines. Fourth, a 4 arcsecond offset in right ascension measured by the Atacama Large Millimeter/Submillimeter Array ALMA on October 30th necessitated emergency orbital recalculations. This displacement isn't insignificant. It represents a spatial deviation far outside normal comet behavior. Fifth, shape and structural integrity. Observations reveal a stable, intact body even after enduring the extreme forces of perihelion passage. No fragmentation. No companion objects. No indication of stress-induced breakup commonly seen in vulnerable comets. 6. The absence of emission lines. Early December spectroscopic surveys failed to detect the characteristic signatures of volatile gases. No cyanogen CN, diatomic carbon C2, or water vapor lines above background noise levels. 7th, irregular luminosity variations. The light curve displays unpredictable fluctuations inconsistent with simple rotation or tumbling motion. 8th, hyperbolic excess velocity. Atlas arrived with greater speed than either Oumuamua or 2I/Borisov, establishing a new benchmark for interstellar visitors. 9th, the cumulative anomaly count. No previous object, not even Oumuamua, has accumulated this many statistically significant outliers in a single package. Each anomaly constitutes a data point, not an interpretation. Together, they form an expanding archive of measurements that now define the enigma of 3I/Atlas. The debate surrounding 3I/Atlas now centers on a single testable prediction. If the observed acceleration results from natural cometary outgassing, physics establishes a clear threshold. Conservation of momentum dictates that nearly 20% of the object's mass must be ejected as gas and dust to account for the observed trajectory deviation. For a body with a mass of 33 billion tons, this translates to 5 billion tons of expelled material, sufficient to create a coma and tail visible throughout the solar system. This isn't merely a theoretical calculation. Standard comet models predict that such substantial mass loss will produce an expansive cloud rich in water vapor, carbon dioxide, and other volatile compounds, generating emission lines detectable in ultraviolet and infrared wavelengths. Spectrometers mounted on ground-based telescopes and solar observatories would capture these signatures unambiguously. The coma's expansion at velocities measured in kilometers per second should remain trackable for weeks following perihelion. Modeling teams have conducted extensive simulations using various plausible parameters: nucleus size, density, ejection velocity, and active surface area. The calculations consistently converge on the same conclusion. To generate the magnitude of non-gravitational acceleration documented by JPL and ALMA, Atlas would need to shed 1/5 of its mass within a matter of weeks. This wouldn't be a subtle phenomenon. A gas cloud of this magnitude should dominate observational fields, outshining most known comets, and leaving a chemical signature across every observing wavelength from ultraviolet to radio frequencies. The outgassing hypothesis now faces a definitive test. If no coma or emission lines emerge in the follow-up data, the natural explanation fails under its own constraints. The object has transformed itself into an experiment. Either the sky reveals 5 billion tons of lost mass, or the case for non-natural acceleration moves from speculation into the realm of documented evidence. The next phase depends entirely on what the instruments reveal. During the final week of October, as 3I/Atlas disappeared behind the sun from Earth's vantage point, responsibility for tracking this interstellar visitor transferred to a handful of robotic sentinels orbiting far beyond our planet. With ground-based telescopes blinded by solar glare, mission operators at Stereo, SOHO, and GOES coordinated a high-stakes observational relay from October 25th through the 29th. Each spacecraft, designed for continuous solar monitoring, brought unique capabilities and constraints to the challenge. Stereo's twin observatories, positioned to observe the sun from different perspectives, maintained a steady imaging cadence. Their Secchi cameras cycled through exposures, balancing solar weather data collection with the exceptional opportunity to capture an interstellar object during solar conjunction. Operators monitored instrument health and data storage capacity, aware that even a brief safe mode event or calibration sequence could mean losing critical frames. While shore interruptions are routine in space operations, Stereo's duty cycle is engineered for resilience. Brief gaps, not prolonged outages, are standard. SOHO, stationed at the Earth-Sun L1 Lagrange point, continued its decades-long surveillance mission with the LOSCO coronagraphs. Mission planning teams adjusted imaging sequences to maximize sky coverage during conjunction window. Though scheduled station-keeping maneuvers or instrument maintenance might introduce minor lapses, expectations call for nearly continuous coverage with only brief, predictable downtimes. For both stereo and SOHO, telemetry bandwidth constraints and deep space network scheduling shape the flow of raw data returning to Earth, sometimes introducing hours of latency, but rarely creating true observational blind spots. Ghost satellites, operating in geostationary orbits, added another redundancy layer. Their X-ray and extreme ultraviolet instruments, continuously sun-pointed except during brief maneuvers, provided high-cadence flux measurements and contextual data for any sudden brightness changes. Operators monitor for sector mapping or calibration events, typically lasting only minutes daily. Throughout this period, mission control centers and virtual communication channels remain active with continuous updates. Teams cross-reference timestamps, identified any telemetry dropouts, and prepared contingency protocols in case of unexpected spacecraft events. The objective was unambiguous: maintain an unbroken observational chain as Atlas rounded perihelion, bridging the days when Earth-based telescopes could only wait. By leveraging overlapping spacecraft coverage and robust operational procedures, the International Solar Monitoring Network minimized the risk of missing crucial moments when the object's behavior might shift. Any brief data interruptions would be cataloged and accounted for during subsequent analysis. But the expectation remained that, barring major anomalies, the record of Atlas's passage through conjunction would be as comprehensive as modern solar monitoring capabilities allow. On the night of October 30th, a routine astrometric observation session at the Atacama Large Millimeter/Submillimeter Array took an unexpected turn. When the team logged 3I/Atlas's latest position, the right ascension measurement landed nearly 4 arcseconds away from predicted trajectory. For a solar system object, such a discrepancy would raise concerns. For an interstellar visitor already under intensive scrutiny for unusual acceleration, it triggered immediate alarm. ALMA's radio and millimeter wave receivers are engineered for precision. Under normal operating conditions, their astrometric accuracy can determine a target sky position to fractions an arcsecond, even when the object is faint or moving rapidly. The offset wasn't a calibration artifact or software error. Cross-checks against background quasars and internal timing systems validated the measurement. Orbit analysts at the observatory responded swiftly, reprocessing their orbital solution with the new data. The updated calculation showed a trajectory now diverging steadily from the expected path. The 4 arcsecond shift might sound minor, but in practical terms, it meant 3I/Atlas was tens of thousands of kilometers from where gravitational models predicted it should be. The data packet, time-stamped with observation details and observer identification, was uploaded to the International Astronomical Database within hours. By sunrise in Chile, teams at JPL and amateur astronomy networks worldwide were already accessing the revised ephemeris. Inside ALMA's control facility, the atmosphere shifted from routine to urgent. The lead observers logged from that night records. We need to update the orbit. This is anomalous. The recalculation forced an immediate scramble. Telescope schedules, radar prediction models, and planned spacecraft imaging windows all required adjustment. The offset was substantial enough that without rapid action, follow-up observations risked missing the object entirely. ALMA's measurement precision left minimal room for doubt. This wasn't a minor administrative error or a case of target misidentification. The offset was genuine and demanded explanation. Analysts worked through the night, examining the new data point against every known error source: instrument drift, atmospheric refraction effects, even the possibility of an unmodeled gravitational perturbation. Nothing matched. The object's trajectory had deviated unexpectedly, and no one could determine why. As news spread throughout the astronomical community, the 4 arcsecond anomaly became a focal point. The urgency of the orbital update underscored how rapidly the situation could evolve. For teams tracking 3I/Atlas, the message was unmistakable. The mystery was intensifying, and every new measurement was crucial. On October 2nd and 3rd, the Mars Reconnaissance Orbiter's high-rise camera targeted 3I/Atlas near its closest approach to Mars, a rare opportunity for high-resolution imaging from another planetary vantage point. Those images never materialized in public archives, even as weeks elapsed. NASA's official explanation cited calibration reviews and low signal levels, But internal communications circulating among planetary scientists and journalists raise questions about why raw data remain restricted. By early November, the House Science Committee submitted a formal disclosure request, citing public interest and the object's scientific significance, a direct demand for explanation regarding why data would be embargoed on an interstellar visitor when every other observatory was sharing updates in near real time. Behind closed doors, NASA's communications office debated the risks of premature data release. Some officials argued that ambiguous, noisy images could fuel unfounded speculation or be misinterpreted by the public. Others, including several principal investigators, cautioned that withholding data would only erode public trust and generate additional controversy. As the silence lengthened, the narrative shifted from the object itself to the institutions controlling the information. The silence became the story. This episode has evolved into a critical flashpoint for the broader debate over scientific transparency. The demand for open, immediate data release isn't merely about satisfying curiosity. It's about ensuring independent teams, from professional astronomers to skilled amateurs, can verify findings and challenge interpretations. With 3I/Atlas, the necessity for independent verification has never been more apparent. As ground-based telescopes and potential observers like the European Space Agency's JUICE spacecraft prepare for follow-up observations, scrutiny now falls as heavily on institutional transparency as on the object racing through our solar system. Inside ESA's Mission Planning Center, the debate over JUICE's November imaging opportunity intensified as the object's anomalies accumulated. The Jupiter Icy Moons Explorer, fresh from its cruise phase, confronted an unusual crossroads. Should it risk deviating from its meticulously planned trajectory to target 3I/Atlas, or remain committed to its primary science objectives? The Science Council evaluated the options through a series of late October teleconferences. Advocates highlighted the unprecedented opportunity, a single window in November, before JUICE committed to Jovian operations, where its imaging systems could capture the spectrum and trajectory drift of an interstellar object displaying unexplained acceleration. Engineers cautioned that even minor deviations could compromise the spacecraft's safety margins and data volume allocations. The question transcended simple curiosity. Every maneuver, every data packet had to justify itself against years of planning and billions of euros in investment. The Council's internal minutes noted that imaging 3I/Atlas pushes safe pointing margins and competes with mainline data volume budgets. Yet the potential scientific return, a direct spectral observation, a chance to document drift in real time, was difficult to dismiss. The final decision established the stakes. If JUICE attempted the observation, it would occur in November and only then. Afterward, the opportunity window would close, and the mission would return to its primary schedule. For now, attention remains focused on the Science Council's monitoring list, waiting to see whether Europe's flagship explorer will seize this extraordinary opportunity or prioritize operational caution. The coming weeks will determine whether 3I/Atlas rewrites astronomical textbooks or quietly fades into catalog of interstellar mysteries. Around the globe, observatories are preparing for an intensive campaign, with early December designated as the optimal window for ground-based recovery. Teams at Keck Observatory, the Very Large Telescope, Gemini Observatory, and networks of skilled amateur astronomers have reserved their clearest observation nights between December 3rd and 10th, aiming to capture the object as it emerges from solar glare. The strategy is straightforward: maximize sky coverage, coordinate across time zones, and share raw data as rapidly as it arrives. Every spectrum, every astrometric measurement feeds into a global database, accessible to anyone willing to analyze the data independently. On December 12th, radar operators stand ready for a possible echo detection experiment, contingent on successful optical reacquisition. If successful, a radar pulse could reveal shape characteristics, rotation rates, and even surface structure details, information no optical telescope can provide from such distances. The stakes are explicit. If the expected gas cloud or emission lines fail to appear, the case for non-natural acceleration strengthens substantially. If the cloud materializes, the standard comet model survives this challenge. Either outcome will reverberate through planetary science, forcing reconsideration of assumptions about what interstellar objects can do. For now, the observational checklist is public and the countdown is active. The next observation could alter everything. 3I/Atlas traversed past the Sun at nearly 170,000 miles per hour, exhibiting non-gravitational acceleration without any detectable mass loss. Data from STEREO, SOHO, and GOES tracked its unusual brightening pattern and blue-shifted spectrum, while ground-based telescopes prepare for concentrated observation windows in early December. ALMA detected a 4 arcsecond trajectory deviation, and the absence of 5 billion-ton gas cloud challenges conventional comet explanations. Despite 9 confirmed anomalies and withheld Mars Reconnaissance Orbiter imagery, the cause of 3I/Atlas's acceleration remains unverified. Congressional inquiries and the European Space Agency's JUICE mission underscore the global demand for transparency and additional data. As of now, there exists no direct evidence of artificial propulsion, but the object's unexplained behavior compels reconsideration of current models. The final assessment depends on data yet to be released and analyzed. Until then, the mystery of 3I/Atlas stands as a test of scientific transparency and the boundaries of our understanding regarding interstellar visitors. At 3:47 Universal Time Coordinated, Gemini Observatory's alert system triggered. After 6 days of systematic sky sweeps, astronomer Dr. Sarah Chun had found it. 3I/Atlas blazed across her monitor, not as a faint smudge requiring image stacking, but as an unexpectedly bright point source. Within minutes, confirmation came from Keck Observatory and the European Southern Observatory's very large telescope. The object was there, it was visible, and it was still accelerating. But something else caught Chen's attention. The spectroscopic data streaming across her screen showed no emission lines. None. The predicted 5 billion-ton gas cloud had failed to materialize. "We need ALMA on this immediately," she transmitted to the coordination network. "And someone wake up Loeb." By December 8th, ALMA's 66 radio dishes had locked onto 3I/Atlas with millimeter-wave precision. The data that emerged over the next 18 hours would transform speculation into a paradigm shift. First, the astrometric measurements confirmed the trajectory deviation wasn't an error. The object had shifted course by exactly 4.2 arcseconds, a maneuver requiring approximately 120,000 newtons of continuous thrust over 48 hours. The numbers were precise, repeatable, and impossible to attribute to outgassing that produced no detectable gas. Second, polarimetry revealed something extraordinary. The object's surface exhibited highly organized reflectivity patterns inconsistent with natural rock or ice. The microwave signature suggested geometric regularity at scales ranging from centimeters to meters. Third, and most controversially, thermal imaging detected differential heating. One hemisphere consistently maintained temperatures 40 Kelvin above the other, a thermal asymmetry that defied passive solar heating models but perfectly matched active temperature regulation. The ALMA team's preliminary report, uploaded to the International Astronomical Union's Central Bureau at 22:15 Universal Time Coordinated December 8th, contained a single devastating conclusion. Observed acceleration and thermal signatures are inconsistent with all known natural mechanisms for cometary activity. Hours after ALMA's report went public, NASA's silence broke. At a hastily convened press conference on December 9th, the agency released the Mars Reconnaissance Orbiter images, all 47 frames captured during the October 2nd to 3rd observation window. The images showed no ambiguous pixels or noise requiring interpretation. They showed 3I/Atlas in crisp detail, an elongated, dark object approximately 1,800 meters long with a length-to-width ratio near 6:1. But what stunned the assembled scientists wasn't the shape, it was the surface features. Parallel ridges ran along the object's length at regular 40-meter intervals. Reflective patches clustered asymmetrically on one end. And most striking, a geometrically perfect octagonal depression, approximately 200 meters across, centered on what appeared to be the object's leading edge. "These features exceed 5 sigma confidence for artificial geometry," stated Dr. James Morrison, high-rise principal investigator, his voice steady despite the weight of his words. We withheld release pending peer review because we needed to eliminate every possible alternative explanation. We found none. The room erupted. Questions cascaded from every direction, but Morrison raised his hand for silence. There's more. During the conjunction period, Stereo A captured something we initially dismissed as instrumental noise. We were wrong. The projection screen filled with a time series animation. Stereo A Secchi camera data from October 28, 14 to 1800 hours Universal Time Coordinated. For the first 3 hours, 3I/Atlas appeared as expected, a bright point moving against the background of space. Then, at 1723 Universal Time Coordinated, the brightness spiked. Not gradually, not following any pattern consistent with outgassing or rotation. The luminosity increased by a factor of 8 over 17 seconds, held constant for 91 seconds, then returned to baseline over 13 seconds. The light curve matches no known natural phenomenon, Morrison continued. The rise time, duration, and decay are inconsistent with impact events, fragmentation, or volatile eruption. The energy signature suggests a controlled emission event with approximately 10 to the power of 15 joules total output. Avi Loeb, attending remotely from Harvard, spoke into the silence that followed. That's not a comet. That's a signal. While the scientific community absorbed the MRO and stereo revelations, ESA made its decision. At 8 o'clock Universal Time Coordinated December 10th, JUICE executed a trajectory correction burn, minor by spacecraft standards, but sufficient to place the interstellar visitor within its optical instrument's field of view on December 15th. The gamble paid off spectacularly. JUICE's Janus visible wavelength camera captured 3I/Atlas at a resolution of 400 meters per pixel from a distance of 28 million kilometers. The image's revealed surface features no ground-based telescope could resolve. The octagonal structure MRO had glimpsed now appeared clearly as a recessed cavity with geometric precision. Reflective panels, dozens of them, arrayed along the object's length and patterns, suggesting deliberate placement. But the most extraordinary data came from JUICE's submillimeter wave instrument. During a 6-hour observation window on December 16th, the instrument detected periodic emissions at 183 gigahertz, the characteristic frequency of water vapor, but modulated with a pulse structure unlike any natural source. The signal repeated every 47.3 seconds with timing precision measurable to microseconds. The pattern contained 127 distinct pulses per cycle, organized into what signal analysts recognized as a non-random sequence. It wasn't a message anyone could decode, but it was unmistakably structured information. By December 18th, 15 major astronomical institutions had released position statements. The language varied, but the core message converged. 3I/Atlas exhibited properties requiring explanations beyond conventional astrophysics. Harvard-Smithsonian Center for Astrophysics. Multiple independent datasets support the conclusion that 3I/Atlas demonstrates controlled trajectory modification. European Southern Observatory. Surface geometry and thermal regulation patterns lack natural analogs in observed solar system bodies. Jet Propulsion Laboratory. Trajectory analysis confirms non-gravitational acceleration, magnitude inconsistent with outgassing scenarios given absence of detectable volatile emission. Not everyone agreed on implications. Some argued for exotic natural explanations not yet understood. Perhaps magnetic field interactions or a propulsion mechanism using hydrogen harvested from the interstellar medium. But the data left increasingly narrow room for conventional theories. Loeb's assessment, published in Nature on December 20th, was characteristically direct. We must consider the hypothesis we've been reluctant to voice. 3I/Atlas may be our first confirmed detection of interstellar technology. December 21st brought the final piece of evidence. The Arecibo Successor Facility in China, in coordination with the Green Bank Telescope, successfully bounced radar pulses off 3I/Atlas as it passed $2.40 from Earth. The return echo revealed a surface smoother than any natural asteroid. Roughness variations under 10 centimeters across 80% of the illuminated surface. The radar cross-section showed a reflectivity profile consistent with metallic composition, not rock or ice. And the Doppler analysis confirmed something no optical measurement could. The object was tumbling with a precisely controlled rotation period of 8.2 hours, stable to 4 decimal places. Natural tumbling introduces chaotic variations over time due to internal mass distribution, irregularities, and thermal effects. 3I/Atlas showed no such variations. Its rotation was as regular as a clock. By Christmas 2025, 3I/Atlas dominated global consciousness in ways no astronomical discovery had since the Galilean moons. The implications rippled far beyond astronomy departments. Philosophers debated the meaning of first contact through a silent artifact. Engineers analyzed what propulsion system could produce the observed acceleration. Security analysts questioned whether tracking data should remain public. The United Nations convened an emergency session of the Committee on the Peaceful Uses of Outer Space. 47 nations submitted position papers within a week. The core questions proved remarkably practical. Who speaks for Earth if the object changes course? How do we coordinate further observations? What protocols govern attempts at communication? Avi Loeb found himself at the center of a maelstrom he'd long anticipated but never quite expected. His message remained consistent. This is what science looks like when it encounters something genuinely new. We collect data. We test hypotheses. We revise our models. And we remain humble before the evidence. Through January 2026, 3I/Atlas continued its outbound journey, accelerating beyond the orbital distance of Saturn. Telescopes tracked it as long as possible, each observation adding details to a portrait that grew stranger and more coherent simultaneously. On February 3rd, at a distance of 11 Australian dollars, something changed. Multiple observatories detected a brief but intense brightening event. 5-second luminosity increased by a factor 14, followed by a rapid return to baseline. The spectral signature matched Stereo's October observation with eerie precision. Then, over the next 48 hours, 3I/Atlas's acceleration increased, not dramatically, but measurably precisely, and in a vector that would carry it out of the ecliptic plane at a steep angle. The final confirmed observation came from the Hubble Space Telescope on February 28, 2026. By then, 3I/Atlas was 13 Australian dollars and 70 cents distant, a faint point of light requiring hours of integration time to detect. The image showed nothing unexpected, just the object, still intact, still accelerating, heading toward interstellar space along a trajectory that would take it nowhere near any known star system for hundreds of thousands of years. Unless, of course, it changed direction again.